Imagine you have been transported to the future and it's your job to determine if planet Z could possibly have liquid water on its surface. You have a scientific tool known as a phase diagram to help you figure this out. A phase diagram shows the state a substance is in at different pressures and temperatures. Phase diagrams are related to phase changes. You might not be familiar with the scientific term phase change right now, but you've probably witnessed quite a few phase changes in your life. Have you ever noticed frozen petals? Or dew on the leaves of plants? Or steam leaving a pot as you boil water? Well, those are all phase changes, or the change from one state to another state. In this context, the word state refers to a substance's form, solid, liquid, or gas. Let's take a moment to talk about phase changes and give some examples. When a solid changes into a liquid, melting has occurred. Just think about an ice cube melting in a glass. Conversely, when a liquid changes into a solid, freezing has occurred. This is what happened to those frozen puddles. When a liquid turns into a gas, vaporization has occurred. That's why you see water vapor leaving your pot as you boil noodles. A lot of that water leaves the pot as water vapor, a gas. The reverse of this is condensation. This is when a gas turns into a liquid. Think of the dew on the leaves. The gas in the air cooled, and some of it turned into liquid, or dew. This last phase change is probably less familiar, when a solid becomes a gas, or sublimation. If you've ever seen dry ice or solid carbon dioxide, you've probably watched it turn directly into a gas. When a gas turns directly into a solid, deposition has occurred. You might notice this when you drive through fog and freezing temperatures and ice gets on your windshield. So, what does this have to do with finding liquid water on planet Z? Don't worry, I'm getting there. Let's get back to those phase changes. All of these phase changes occur at certain temperatures and pressures. For example, water boils at 212 degrees Fahrenheit, or 100 degrees Celsius, at a pressure of 1 atmosphere. But let's say you wanted to boil water at the bottom of a deep pit that has a pressure of 3 atmospheres. Because of this difference in pressure, water's boiling point would be higher than it is at sea level. But what if you wanted to boil water on top of a tall mountain where there's less pressure? Yep, you guessed it. It's easier to boil water when there's less pressure, meaning the boiling point is lower. So you can see boiling points change depending on factors such as pressure. This holds true for other phase changes as well. So you might be asking yourself, how in the world do people keep all of these pressures, temperatures, and phase changes straight? Well, that's exactly what phase diagrams are for. This phase diagram is going to help you figure out if there's liquid water on planet Z. Since you need to figure out if water can exist in its liquid form on planet Z, let's start by examining the phase diagram for water. The x-axis is labeled T for temperature and the y-axis is labeled P for pressure. You'll notice the graph is separated into 3 parts, the solid, liquid, and gas phases of the substance. Each line separating the different phases is where they are in equilibrium. For example, on the line separating liquid water and solid water, or ice, the water is partially liquid and partially solid. Both phases exist at this point. When you're not on the line, only one phase exists. When you cross the line, there's been a phase change. For example, when you cross from solid to liquid, melting has occurred. Or when you cross from a gas to a liquid, condensation has occurred, but I think you get the idea now. Before we compare water to other substances, let's take a closer look at a couple of points on the graph. First, take a look at the triple point. This is the point where water is at an equilibrium between solid, liquid, and gas. In other words, all 3 phases occur at this point. Next, check out the critical point. Above the critical point, a substance exists as a supercritical fluid. A supercritical fluid is a gas that's really compressed, so it behaves like a gas with some properties of a liquid. You can't turn a supercritical fluid into a liquid without lowering the temperature. Each substance has a unique critical point and triple point. Okay. So, can planet Z have liquid water? Well, first we need to figure out the temperature and pressure on the surface. From our futuristic instruments, we know the temperature is extremely cold and the pressure is really low. So, if we look at the graph, it appears that if there is any water on planet Z, it's probably in the solid or ice form. Excellent job on your first mission! But phase diagrams can all look a little different depending on the substance and the style of the graph, so you'd better familiarize yourself with a few. Some use Celsius, others use Kelvin, and some use atmospheres and others use different units for pressure. Some look really simple, and some are very colorful. It also might be a good idea to compare the water phase diagram to another substance, because who knows what they'll have you looking for next on planet Z. If you compare water to other substances, you'll notice a couple of differences. Let's start by comparing water to carbon dioxide, which is the gas you're breathing out right now. You'll notice the line separating solid water and liquid water slopes to the left. Now look at the same line for carbon dioxide. You'll notice it slopes to the right. So what does this difference mean? Well, it's one way the water phase diagram is different. Water has a unique structure that makes the liquid denser than the solid. Density is how much mass is in a certain volume. Let's take a moment to look at some examples that you've seen but probably never thought much about. Ice floats in water because ice is less dense than liquid water. If you freeze water in a glass jar, it will crack the jar because the ice is less dense, and the same amount of ice takes up more space than it did when it was water. Both water and carbon dioxide have different critical points and triple points as well. Let's look at the phase diagram for carbon versus water. You'll notice that this particular phase diagram has two solid forms, graphite and diamond. You'll also notice the line separating the solid from the liquid slopes to the right, like carbon dioxide. Again, water is fairly unique in that this line slopes to the left. Finally, all substances have different triple points and critical points, so water and carbon have different values for these points. Scientists use phase diagrams to organize a lot of information on one graph. It's handy to know at what temperature and pressure a substance will be a liquid, solid, or gas, as you saw when you figured out there was no liquid water on planet Z. Real-life scientists used a phase diagram for water to determine if there was liquid water on Mars, and they found that it was too cold and the pressure was too low, just like on planet Z. Let's take a moment to review some important ideas. Phase diagrams are graphs with temperature on one axis and pressure on another axis. They are divided into sections that denote which state a substance is in at certain pressures and temperatures. Water is fairly unique because its melting line slopes to the left. Most other substances slope to the right. This is due to water's unique properties that make it less dense as a solid than a liquid. Well, I just heard you're off on another mission. Good luck, and don't forget to take your phase diagram with you.